Hello everyone, so this is a video on roots of polynomials essentially and what they, certain characteristics that they have. Essentially chapter 4. This should help you with the first three exercises, 4a, 4b and 4c. Now I'm not going to prove these results which I'm about to show you because I just want to get through a few questions in this first video. I'm happy to prove these results and actually do some of the challenge questions perhaps in another video after this, but let's just go through some ideas first, yeah? So let's do a polynomial of order 2. Let's talk about polynomials of order 2 first. I'm sure you all know what we actually call those more commonly. We call them quadratics. Now, the general shape of a quadratic is ax squared plus bx plus c equals 0. Yeah? Now, let's say that alpha, and we tend to use Greek letters here. Get good at drawing Greek letters. I'm not brilliant at drawing Greek letters, but you will get better after this chapter, I promise you that. Say alpha and beta solve this equation, i.e. their roots, yeah? So alpha and beta are both numbers which solve that equation, i.e. their roots. That's why this chapter is called Roots of Polynomials. Yeah, roots are just another word for solutions. Okay, what can we say? Well, we can say that alpha plus beta will definitely equal minus b over a. And this is very much related to the old trick we use for factorizing quadratics, which is find two numbers that add to give the middle and multiply to give the final term. Alpha beta is going to be c over a. And those are the rules that you can always use, always, 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 if you know two roots of an equation. Just to quickly show you, I'd like to demonstrate that this actually works. Let's take an equation like 2x minus 1 x plus 2 equals 0. Clearly the roots are alpha is a half, if you like, and beta is minus 2, yeah? If I multiplied that out, I would get 2x squared minus x plus 4x, well, that's plus 3x, and then minus 2 equals 0. Let's just show you that those results hold. Alpha plus beta is clearly minus 1.5. Well, guess what? Minus 3, yeah, minus b over a here would be minus 3 over 2. See, it works. It works. Just to show you it works. It blimmin' works. Alpha beta is going to be minus 1, and alpha beta is c over a, which is minus 2 over 2. Oh, yeah, let me write down c over a equals minus 2 over 2. So it indeed equals minus 1. So big ticks on both accounts there. So just proving to you there that these tricks definitely work. Now, that rule you can use without proof whatsoever whenever you're dealing with quadratic roots of polynomials. Now, the fact is, very rarely do they set questions. Well, I think it's quite rare, perhaps even very rare, to set questions about the roots of polynomials when you're only working with a quadratic, because it's far more useful. With quadratics, we already know them inside out and round and round. We know exactly how to solve them, how to find the minimum vertex, etc., etc., etc. So they tend to give you these questions on cubics or quartics. Yeah, they're far more common. So let's talk about polynomials order 3 now. Now there is a lovely pattern here which emerges. Polynomials order 3, they're obviously cubics. Now let's define it as ax cubed plus bx squared plus cx plus d equals 0. And let's say the roots, let the roots be, in other words, the solutions, alpha, beta, and gamma. Now, gamma you draw like that, or I draw it like that. Be careful though with gamma. Delta and gamma can end up kind of looking really quite similar. So make sure, and gamma comes before delta, by the way, in the Greek alphabet. Make sure that you write gamma that's not too similar to alpha and not too similar to delta. It can end up being a bit of a headache, that. Just a little warning for you there. Okay, so what can we say about the roots this time? Well, the sum of the roots, alpha plus beta plus gamma, that is going to be equal to minus b over a again. Yeah, so it works the same way. You always start at minus b over a. The sum is always equal to minus b over a. Now we get the sum of the pairs, of the product pairs as they're called. Alpha beta plus alpha gamma plus beta gamma. Everything gets multiplied by everything else once, yeah? So beta's been times by alpha and gamma. Alpha's been times by beta and gamma's been times by alpha and beta, yeah? Okay, that equals C over A. But if we times them all together once again, alpha, beta, and gamma, if we times them all together, well, that equals minus D over A, yeah? And those are the rules for cubics. Now, there is a slightly more convenient, if slightly more rough and ready, notation for this. You sometimes just write sum of alpha for this one and sum of alpha beta, indicating that you're just multiplying the pairs together for that one. We don't write a sum of a sigma for this one because it's all just getting times together, but that's just an alternative notation to let you know. Now contrast this with polynomials order 4, and I'm going to do that question down there in a second. Polynomials order 4, they're obviously called quartics. Let's write those out as ax to the 4 plus bx cubed plus cx squared plus dx plus e, yeah, it goes on forever this, doesn't it, equals 0. Well, let the roots be, well, we need 4 roots this time. And remember, this chapter works for complex numbers as well as real numbers. Alpha, beta, gamma, and delta. Yeah, you see my gamma's starting to look a little bit like my delta there. Let me make it look a little bit more distinguished. Yeah, it's not easy on a tablet as well. They normally make it more like that. I need to make a conscious effort to make my gammas more of a little, very tiny little dot at the end. If you look in the book, you'll see that's the case when we go to a question in a minute. Okay, so these are the roots. What do we have? Well, we have the sum of the roots. To use that informal notation again, sum of alpha is just to stop us writing alpha plus beta plus gamma plus delta down, but you can just write sum of alpha. Well, that's minus b over a again. And then you just start and you alternate the signs. The sum of the product pairs, alpha, beta, we could write it down like that, and this is the thing, there's a lot more to do here because you've got alpha, beta, and this is why we have the shorthand notation, alpha, gamma, alpha, delta, try and be systematic, plus beta, gamma, because we've already done beta, alpha, beta, gamma, plus beta, delta, and then the last one we haven't done is gamma, delta. The sum of all those is C over A. Yeah, you can see why we have the shorthand now. Now, what comes next? The triples, alpha, beta, gamma. No, you don't get this in the formula book. I know what you're thinking. Did we get this in the formula book? No. Well, remember, when you're doing these ones, you should be missing out one letter each time, so there should be 4 of them. Alpha, beta, gamma, plus alpha, beta, delta, plus beta, gamma, delta, plus, which one have I missed out? Alpha, gamma, delta. There we go. That equals minus D over A. These are the important results at the end. And then finally, just times them all together. That equals E over A. Yeah, and yes, this pattern continues for higher order polynomials, and like I say, if I'm going to go about proving it, I might save that for another video. Let's just bear in mind all those facts and try some of these questions. Yeah, and in exercise A, B, and C, you just need to know those facts to get these questions right. Okay, so what have we got? We've got a cubic, so we're dealing with these rules, essentially the ones on the left, and we're told the roots. Now, the roots are alpha, 2 alpha, and 3 alpha. Those are my, if you like, my alpha, my beta, and my gamma in this question. So what do I know here? Well, what do I know? I know that the sum of those roots is going to be equal to minus b over a. So minus b over a, this is the way I normally write it down, is going to be equal to here to be minus 48 over 2, which is minus 24. And don't forget that that equals alpha plus 2 alpha plus 3 alpha. And so what do we have there? We have minus 24 is 6 alpha. Well, that's great. I can see alpha is minus 4. Lovely. I've worked out all the roots now. I know all the roots. Yeah, that means really I could do the rest of the question. I might as well keep using this idea though. I also know that c over 2, yeah, or c over a I should say, just to make it a bit more clear what I'm doing. C over a equals c over 2 in this case. And that's going to be equal to, now these are the product pairs, that one times that one, 2 alpha squared, plus that one times that one, 3 alpha squared, plus that one times that one, 6 alpha squared. So c over 2 equals, by the look of it, 11 alpha, 11 alpha squared, is that? Well, the good news is I know alpha is 4, minus 4, so alpha squared is going to be 16. So I can work out c now. C equals 2 times 11 times 16, and that means that c comes to 352. And lastly, I can use the last result, which is that minus d over a, which clearly here is minus d over 2. Well, that's going to be equal to all of the roots times together, which simply equals 6 alpha cubed, does it not? So there we go. That's what we're timesing together here. Give myself a bit more space. So I'm going to get minus d equals 12 alpha cubed. Alpha cubed is minus 64. So minus d equals 12 times by minus 64. And I think that means that d comes to 768. Let me just check that on a calculator. You know what I'm like. 12 times 64. Should really get that right in my head, but yes, I did. Thank God for that. Okay, and that's a typical cubic question. Now, I'll show you one of the tougher questions in a second, which is more like exercise 4D, which is coming up, and I want you to sort of get warmed up for that. But first, let's do a quartic one. Okay, so I've just pinched this from the textbook. I think this comes from exercise 4C, question 12, I think. Let's have a little look at this one. So this one's going to be a little bit tougher, but we can just use the principles each time. Can use the principles each time. Another principle I'm going to use is that roots occur in conjugate pairs in polynomials, yeah? Now that's particularly useful if one of the roots is a complex number. If one of the roots is a complex number, as it is here, we're told that the root for gamma, see that's how they draw gamma, much better than my gamma, like that, yeah? Gamma is 3 plus I, and delta is gamma star. Now, do you all remember what this star means? It means the conjugate. Never forget that. It's really, I've found students in the past have often forgot this little piece of notation. If Z is A plus BI, then Z star is A minus BI. Never forget that handy piece of notation. It is regularly forgotten. It really is. And it's not to be forgotten. So don't forget it. There we go. That's my rant over. So we immediately know that delta is 3 minus I. I would have said that straight away anyway. As soon as you tell me one of the roots is 3 plus I immediately know another root is 3 minus I. Dead useful that, yeah? So delta is 3 minus I, gamma is 3 plus I. And we've got to show that something is true. Yeah. Now, I tend to start these questions because I can immediately see this is about roots of polynomials. I tend to start them by writing down my facts. Yeah. Now, remember, minus b over a, which is going to be 19 over 4, that is going to be equal to alpha plus beta plus gamma plus delta. Yeah. Well, that means that 19 over 4 equals alpha plus beta plus, what's gamma plus delta? It's 6. If you ever add a complex number to its conjugate, you just get double the real component of the original complex number. So yeah, we end up with 19 over 4 equals alpha plus beta plus 6. You know what? I think I can deduce that fact now. Because if I just times everything by 4, I'm going to get 19 equals 4 alpha plus 4 beta plus 24, and then subtract, I get 0 equals 4 alpha plus 4 beta plus 5. So I've shown that that's true. Okay, so I've used my minus b over a. Now, if I look at this, yeah, particularly because the c over a and the minus d over a, they're both going to have p's and q's involved. So I want to use the e over a fact in my, where's my write-up? Yeah, I want to use this last fact, basically times the roots together, and you get the term independent of x divided by the coefficient on the highest power, which is x to the 4. So we're going to do this. We're going to do alpha beta. Well, let's write it down the same process I did before. I could say minus b over a equals that, c over a equals that, minus d over a equals that. E over a, though, equals alpha, beta, gamma, delta. And in this case, oh, I normally write it down. Sorry, I'm just trying to be consistent with the way I've been notating it. E over a is simply, in this example, 10 over 4. Yeah, and that is equal to alpha, beta, gamma, delta. Happy with that? Oh, but hang on a second. Gamma delta is 3 plus I times 3 minus I. Oy. Sorry, I've messed up slightly. And that equals 9 minus 3i plus 3i, they cancel. 9 minus I squared, which is 10. Yeah, because 9 minus I squared is 9 minus minus 1, which is 9 plus 1, which is 10. So we get 10 over 4 equals AB times 10. Times it all by 4, you're going to get 10 equals 10 alpha beta. Oh, equals 40 alpha beta. Beg your pardon. And so we're going to end up with a quarter equals alpha beta, which is easily rearranged into 4 alpha beta minus 1 equals 0. That easily rearranges into that. Okay, so we've proved the first two results and we've got 2 marks. Seems almost a bit stingy only giving 2 marks for that, but there we go. Hence, find all the roots of the quartic equation and find the values of p and q. Well, what I'm going to do for this one is I'm just going to look at these 2 equations and think to myself, they're 2 equations with 2 unknowns. So I can solve them simultaneously and I'll immediately have the values of alpha and beta, which means I'll have all the roots, alpha, beta, gamma, delta, because I've already got gamma and delta. I just need alpha and beta. And if I've got alpha and beta, I'll be able to deduce p and q using a couple of approaches, I suppose. That's the thing with these questions. There's often lots of ways of doing it. Sometimes slow ways, sometimes long ways. Yeah, so look out for the cheeky way of doing it. Okay, so what do we get here? We get, if I rearrange this, I can rearrange it into, well, clearly alpha beta is a quarter, and so alpha is 1 over 4 beta, or if you like, beta is 1 over 4 alpha. I think I prefer that. It doesn't really matter. Plug it into here. I'm going to get 4 alpha plus 4 times 1 over 4 alpha plus 5. That's going to give me 0 equals 4 alpha plus 1 over alpha plus 5. That's a quadratic in disguise. Sorry, let me just move up, give myself some more space. Times by alpha, 4 alpha squared plus 5 alpha plus 1. Factorize. Yeah, there's a bit of work in here. Okay, that's my feeling. It's going to be 4 alpha and alpha. It could be 2 alpha and 2 alpha. I've probably got it wrong, but let's have a go. Here you'll see how bad I am at factorizing. Plus 1 and plus 1. Oh, look, I've done it the first time. Well, maybe I'm not that bad. So alpha equals minus a quarter, or alpha equals minus 1. You're going to wonder, why have I got 2 different alpha values? Well, watch. Beta times by alpha is a quarter. Using this, I can just say beta is minus 1 or beta is minus a quarter, yeah? Because if I times those 2 together, I get positive a quarter. If I times these 2 together, I get positive a quarter. In other words, the 4 roots are, drum roll, it doesn't matter which order we label them in, but 3 plus I mean, they've called theirs, yeah, let's try and do it similar to theirs. If we just take the first case, alpha is minus a quarter, beta is minus 1, gamma was, did they say it was 3 plus I? And so delta is going to be 3 minus I. And those are the 4 roots, yeah? Now, what have we got to do left? We've got to find the values of P and Q. Now you've got a choice here. We could use the sums of the product pairs and the sums of the pairs to find it because we already know A and we know all of those. So we could do that. Do you fancy doing that? I'm very happy to do that. The other way we could do it, of course, is we could just using these four roots write it as, you know, Z, are you using x in this example? I think they're using x. X minus a quarter in one bracket, sorry, x plus a quarter in one bracket, x plus 1 in another bracket, x minus open brackets 3 plus I, and x minus open brackets 3 minus I. And I can multiply that all out and eventually get it in the form. I'm going to use the new rules because, that's what we're using at the moment. So what are these rules? Okay, so the sum of the product pairs is going to be equal to, yeah? So let's write that down. So C over A. And C over A in this case, oh, let me just look at the original equation again. They're big questions. So P over 4, this is how I'm going to work out P. P over 4 equals all of the products of these times together. So can I just write down, and you can see why we have these little shortcuts, the sum of the alpha betas. I mean, that just means the sum of the pairs. So P over 4 is going to be a quarter. I've done those two times together, plus minus a quarter. Well, yeah, let's put that down as minus a quarter. Let me just get my rubber out. Oh, so what are we going to do? We're going to have minus a quarter times 3 plus I, but then you're going to have minus a quarter times 3 minus I. I hope the astute among you there will realize that the imaginary components are going to disappear, which is nice. So we've done that one, we've done that one, we've done that one. So we've done 3 of them. We've got 3 more to go. Always count how many pairs you've got to go here because it is easy to mess this up. Now we can do this one, and then lastly we can do the bottom 2. So then we've got minus 1 times 3 plus I, minus 1 times 3 minus I, and then finally 1, 2, 3, 4, 5. We've got the last one, plus 3 plus I times 3 minus I. Now, a lot of these will tidy up really quickly. It looks really complicated and looks like it might take ages, but actually it tidies up quicker than you think. Leave the quarter there. We're going to have minus 3 quarters, minus 3 quarters. The I bits are going to cancel. And minus 3 quarters is minus 6 quarters, or minus 3 over 2. Tick when you've taken care of it. Similarly here, you're going to have like the minus I, but the plus I, so these are going to cancel. So you're going to be left with minus 3, which is minus 6. Tick when you've done it. And then lastly here, we already know that multiplies out to give 10. And so what have we got here at the end? By the look of it, what we got, 4 minus 1.5, 2.5 plus a quarter, 2.75. I make it P equals 4 times 2.75, which is, what is that, 5.5, is that 11? Yeah, P is 11. Similarly for Q, similarly, sorry, Q over minus Q over 4, because remember it's minus B over A, C over A, minus D over A. So it's going to be minus Q over 4, and then we're going to do the triplets. So minus Q over 4 equals the triplets times together. Well, we've got our 4 roots there. Let's have a go at this. We're going to have alpha, beta, gamma, which is a quarter times 3 plus I. And then we're going to have alpha, beta, delta, which is a quarter times 3 minus I. And then we're going to have these two times by one of those and these two times by the other one. So minus a quarter times by 3 plus I times by 3 minus I. And then minus 1 times by 3 plus I times by 3 minus I. This is really good practice, this topic, for developing a systematic approach. It really is, which is something I think I was pretty lousy at, to be honest, when I was doing maths when I was younger. I was a real kind of scatterbrained. I still am, you probably noticed. But it pays to be orderly and structured in your life. God, it's taken me years to recognize that fact. And I'm still not very good at it. Once again, they're going to cancel and you're going to get 3/4 plus 3/4, which is, why am I finding that hard? 3 over 2. So I've dealt with these two. Here, we already know that equals 10 and that bit equals 10. So we're going to end up with minus 10 over 4 minus 10. So what does this actually equal? Let's try not to mess this up at the end. I bet you if I mess this up when I check the answers after it in the video, you I bet you it'll be this bit I mess up. Anyway, here we go. We've got 1.5. We've got, what is that? Minus 2.5. And then we've got minus 10. So 1.5 minus 2.5 is minus 1. Minus 1 minus 10 is minus 11. So we're going to get Q is 44, I think. Okay, there we go. Q is 4 times P. What about that? Okay, so that is how you answer that part. At the very, very end, I think what do they want you to do? I might even skip this bit. Show these roots on an argan diagram. Let's show the roots on an argan diagram. I shouldn't have said that. I might even skip this bit. I'm giving you the impression that it's okay to skip parts of a maths question. That is shocking. But let's be honest, it's not difficult. It shouldn't be difficult. We know the roots. We've just got to represent them on an argan diagram. They should be nice and symmetrical. Okay, you get reflective symmetry in the x-axis anyway, because roots occur in conjugate pairs. So we're going to get 3 plus I. Let me do this in a different colour. At least I can enjoy myself then. 3 plus I, 3 minus I. You'll always have that reflective symmetry in the real axis. And then was it minus a quarter? So can I, yeah, denote them with little crosses? It's nice showing them with little crosses. I notice a lot of books do that. Minus a quarter and minus 1. Yeah, and then I can just say 3 plus I, 3 minus I, minus a quarter, minus 1. They will always have reflective symmetry in the real axis and not the imaginary axis because, yeah, you've got roots occurring in conjugate pairs. Okay, okay, that was that one done. Let's show you a difficult one though. That one was quite difficult, but there are ones which end up even more difficult, and this is more like what you're going to get in exercise 4D. This is a difficult topic to self-teach. I'd say it's just as difficult as the what we were doing the complex numbers chapter with the loci. It's just as difficult as the loci, this kind of stuff. So let's see if we can do this. Okay, question 8. Now, this is about looking for patterns, yeah? Part A is not too difficult. It's just find that, that, and that. Well, the sum of alpha, as I might call it, that's what they've asked us to find first, which is alpha plus beta plus gamma. I wouldn't normally write it down. I normally write that down to avoid writing that down. Well, that is simply minus b over a, yeah? Which in this case is 5 over 2. So there we go. I've done the first part. Sum of the pairs, well, that's c over a. And that's going to be 11 over 2. And them all times together, well, that's going to be minus d over a. And that's going to be 9 over 2. There we go. They're all over 2. They're all 0.5s. How about that? Okay, and that's part A done. That will help us with part B. Okay, how are we going to do part B? Well, let's have a look at this first one. It says, oh, hence find the reciprocal roots. How are you going to do that? Well, if you look at this, what would happen if we tried to add all those fractions together? We'd need a common denominator, which will be them all times together. And then we'd have that one times beta and gamma, that one times alpha and gamma, and that last one would be times alpha and beta. Well, look at this. We've got the sum of the pairs over the product of all three. The sum of the pairs is 11 over 2. The product over 3 is 9 over 2. And so you're going to get 11 over 9. And that's it. That's all you need to do. Done. Boom. We've done the first part. Now, that's a relatively easy one. They get a bit more obscure. This is a good example. Alpha squared plus beta squared plus gamma squared. This is where this topic gets a bit more difficult. And you need to do a few of these questions to get used to the difficulty as well. Right. The way I'm going to think about this is I'm going to think, well, hang on a second. If I times alpha plus beta plus gamma, and I use little grids for this. Let me put the plus in there as well. Times by itself, alpha plus beta plus gamma. Oh, almost off of my screen. Let me give myself a bit more space. This is a algebra heavy, this chapter. I'm sure you've realised that. Yeah, it is. It's not just algebra heavy. It's algebra. It's a incredibly heavy algebra. Alpha squared, beta squared, gamma squared. You get that down the middle. So you get alpha squared plus beta squared plus gamma squared. But what else would you get? You get an alpha beta here and an alpha beta here. You get an alpha gamma there and an alpha gamma there, and you get a beta gamma here and a beta gamma here. In other words, this is the same as alpha plus beta plus gamma all squared minus all of these doubles, these two alpha betas, two alpha gammas, and two beta gammas. So I need to take away 2 times alpha beta plus beta gamma plus alpha beta plus beta gamma plus alpha gamma. Yeah, sorry, I wasn't very systematic there, was I? Apologies, I wasn't doing it in the traditional order. Okay, so that is how you do this. That is hard. That is hard. Yeah. Now, what is alpha plus beta plus gamma? Because we're trying to relate it to these 3 results. Well, that's just the sum here. That's 5 over 2, all squared. And then I'm going to take away 2 times 11 over 2. So I'm going to be doing 25 over 4 minus 11. And 25 over 4 minus 11 is minus 19 over 4, I think. So that's 44 over 4. 25 minus 44 is minus 19, I think. So yeah, you get minus 19 over 4. And I've done it. Okay, now let's do part 3. Part 3. Okay, this is probably going to be even more awkward, slightly more awkward, a bit more awkward. It's worth an extra mark. I can't believe they're only worth 2 marks, but there we go. That's further maths for you. You don't get thrown marks like you do in GCSE or AS or A2 maths. You have to work for those marks. Okay, so alpha minus 1, beta minus 1, gamma minus 1. Really, with this one, just multiply it out carefully. Don't worry. Keep telling yourself it's going to be okay. I'm just going to do the first 2 brackets. Alpha beta minus beta plus 1. And I'm going to times that by gamma minus 1. If I times it all by gamma first, I get alpha beta gamma. Cool, I can deal with that. Minus alpha gamma minus beta gamma plus alpha, gamma, sorry. Minus alpha beta minus, plus alpha plus beta minus 1. So let's just put that in a slightly easier to read order. We've got alpha, I'm starting to talk nonsense. Let's put that in a slightly easier to read order. Alpha beta gamma minus alpha gamma minus beta gamma minus alpha beta. That's the sum of the product pairs made negative. And then plus alpha plus beta plus gamma. That's just the sum of the roots, minus 1. Now we've got all of those. Alpha, beta, gamma, let's just remind ourselves what they were. Alpha, beta, gamma was 9 over 2. Then we're going to be taking away the product pairs, which is 11 over 2. And then we're going to be adding the sum, which was 5 over 2. And then we're going to be taking away 1. Well, what do we get here? 4.5 minus 5.5 minus 1. That's plus 2.5 is 1.5. Minus 1 is 1/2, I think. Okay, there we go. That completes it. Any mistakes, feel free to email me and let me know that my job is on the line. Okay, thanks very much for listening. And yeah, keep up the hard work. Well done.